comparison of implicit and explicit.
Excuse me, could you please,
yes, hello.
Quickly explain the Laplacian operation? I didn't fully understand it on
The Laplacian, yes.
Yes, so
That
it's
is
basically the second order derivative of the gradient, but if you could please further explain, it would be highly appreciated.
Right, that's a good question. The Laplacian is not so. Is the gradient clear? So here we have some function. We are typically discussing it in terms of a temperature. Right, and the gradient is basically telling us how does this temperature change. You can imagine you're looking at the temperature in your room along x, y, and z directions. And then the gradient tells you where does your temperature rise quickest. Does that make sense? This is what
yes.
This upside down.
I understand the basics of the gradient.
Right. That's important not to confuse here. Right. The gradient is really a vector, depending on the input, how many input dimensions I have, and the Laplacian is not a vector anymore. That's again a single number. Say my temperature, and right, it basically contains all the three second derivatives added up. So I think the gradient is one of these is very intuitive. It's this direction where things change fastest. The Laplacian is a bit less intuitive. It's more like a curvature, and it looks at the curvature along x, y, and z, all added up along all directions.
Yes, thank you very much. Could you please a bit further explain what is how can we use the Laplacian, like in calculations? For example, there were real world example in the lecture, I think, with the heating of a metal plane, and if I'm correct, the gradient is sort of not the speed of the change, but how much the plane changes over time, and the coefficient is the speed of the change. Is that right, or I fully understand that?
So that's not fully correct. So we're typically treating these gradients as spatial directions. The one important thing that comes into play when looking at kind of real-world examples, we also have time. So we both have space and time, and then the gradient or Laplacian works for those space dimensions, say x and y in this example. And in addition, we have a time component. And here, if you look at this wave equation now, this actually relates derivatives over time, in this case the acceleration, with changes in space. And right, because we have this mix of space and time, that's now really even in 1D already a PDE, a partial differential equation. And here now we have this Laplacian, right? This is the second derivative. And in this wave equation, it actually tells us now the second derivative over time, meaning the acceleration, is actually now equal to this part, or acceleration minus this should be 0. But you could just bring this to the other side here. Then you'd have second derivative of u is equal to c square Laplacian of u. Intuitively meaning I accelerate in some point x, y in space, my value of u, depending on how much curved my function is. So if I have a very sharp peak, then I get a large value here, meaning a large acceleration, and then basically my point would start shooting, in this case, towards a 0 point, and accelerating with c squared times the curvature of this u. Or yeah, in the exercise, you can actually look at this diffusion example in more detail, where we only have a first derivative here. It's a bit simpler, but here for the slides to go through this, we're looking at the second one. Yeah, figuring out these expressions, that's actually quite involved in practice. That's not easy to do. We're looking at all kinds of existing or toy examples. Figuring out how to set up these equations that typically requires a lot of understanding, and that's what physicians 1 and 200 years ago were struggling with a lot to formulate nature in terms of these relationships. And for all simpler effects, this is by now basically done. There's not much to discover, but we're dealing also mostly with actually solving these computing solutions in the computer if we have one of these as input. Does that answer the question, or?
Yes, thank you very much. I understand now. Thank you.
I recommend the tutorial video. I think we have some very nice also additional explanations there, and also I can highly recommend the exercise, which is about also solving this heat or diffusion. I think even if it's a somewhat artificial setup, I think it's interesting to see how this behaves in the computer. So yeah, definitely recommend it. Also, I mentioned here already, but these formulations be very fundamental. So this is also, in a way, a very fundamental and basic topic that applies to many other topics outside of game physics. You'll find this anywhere, from machine learning to particle physics, or sometimes even for there are attempts to formulate things like financial markets also in terms of such equations.
My last question would be about the third exercise. Will there be like a different is it in the third exercise we need to implicitly and explicitly, excuse me, find the solutions?
Exactly. That is actually targeting this aspect, right? Because like you're probably your quest motivated by this more complex implicit one, which so far we haven't really touched, but in the third exercise now you can actually really see how that works. Although we also, from scratch, it would be quite some work. We're giving you a component to do this matrix inversion step. But these are really widespread, so normally you probably wouldn't some existing packages. So it's in a way a realistic setting, but then you can use this to compute the solution. Yeah.
Thank you very much.
Any other questions about the PDEs? Because we also here at TUM, we had some about rigid bodies, so then I would switch to the rigid body topic. So we can, of course, stick around here. I'll just let my microphone run, and then maybe it's also interesting for you. Right, so what were the questions about rigid bodies?
Yeah, first question about collisions with the floor. You mentioned during the lecture that we can simulate it by just setting like 1 divided by mass component to 0 and inertial tensor to 0. So we assume that floor is object 2. And just set its components to 0.
Yeah.
Yeah, but it behaves really strange because we in our group try to do like that. And when we add the gravity, objects just go through the floor, like they collide one time, bounce back up, and eventually they just go through the floor. I don't know. I can show this.
Yeah, no, it's fine. So let me repeat for the online people. So the question is about how to handle collisions with the floor in the rigid body system. And you're right. So the attempt you tried sounds very good. Exactly. You basically treat the floor as an object with infinite mass, right? Then you, because we always have 1 over mass, you get a factor of 0 for these inverse terms. Also, the inertial tensor typically gives you a multiplication of 0. And then if you think about the collision equation, it will basically give you a reflection, right? It's like, if you do it with a wall or so and you give it infinite mass, then anything I shoot against it will just reflect with the same speed and a coefficient of restitution of 1. It will just be fully reflected, right? The mass of the wall means it doesn't move at all, and only everything is transferred back to my other object, whatever it is. So actually, it sounds like it's going right. What does not work out of the box is something like stacking. So for stacking stable resting collisions, because with rigid bodies, we're always doing these fixed steps, these discrete time steps, and that causes additional problems. But we actually get back to that later in the lecture. So that's why also we recommended it for the first exercise with mass spring systems. It actually does work better. But for rigid bodies, we recommend more dealing with in-air collisions.
Or maybe create like walls, not the floor. So
exactly.
Bounce one time and
exactly.
Not end up.
Yes, exactly. I would recommend to look at systems without gravity and more like within walls, things bouncing around.
In case of mass spring systems, it was easy because we shouldn't simulate angular component and we could just take the opposite of velocity. Like if we assume we have a left-handed system, so we just test against like one plane, and if the object is lower than this plane, we just take the opposite of y component of velocity.
Right,
exactly. We just bounce back. But in this case, we should take care about angular components.
Exactly. The problem is this modeling as an object that may not deform, and basically as soon as we have a collision, things are already wrong with rigid. We can just push away, and it's a valid state because mass spring systems can split and deform, and then we resolve it over time. But with rigid bodies, unfortunately, as soon as we have a collision, in a way, our simulation is already in trouble. We have a state that's technically invalid that we somehow need to get out of. And if you have gravity and the floor, then you're basically constantly running into these problems. So you need some additional treatment, and that we'll cover later. Right? Mass spring system basically recovers, but it needs more work to do so, because it needs to compute all these, all the wiggling of the material. Right. And actually this stable stacking in rigid body simulations for a long time was a research topic. I think by now it's relatively solved, but it's still for many rigid body engines, it's one of the trickier parts to get that right. If you look at Bullet or so, there are a whole range of different extensions to treat that in a robust and stable way. So yes, for the second exercise, unfortunately, that will typically not work. At least not well, right? Things will slide or slowly sink through the floor or kind of wiggle around or start moving Also, if you try stacks of objects, then you see they won't stay resting on each other. Yeah, no, but that and maybe we don't warn explicitly enough in the extension in the sign up. But
because in the exercise it's written that trying commenting gravity.
Yeah.
So,
okay. Right. It's an interesting example. But okay, yeah, that's okay. We should Good point. We should warn more clearly that this will not give base results. It's interesting to try and try to some bounces. You should see some effects, but not the ones you would expect from reality. Yeah. Yeah. So those were the questions. Yeah.
I have more questions, but if anyone wants.
I don't. Yeah, go ahead, please. Yeah.
About equation for impulse. In this equation, should we use inertial tensor like the current one, which is calculated as rotation matrix, initial inertial tensor, rotation matrix, I suppose?
Yes.
Or the initial one?
No, this is also, if you think about it, the collision happens in a certain coordinate system, right? And in a certain state. So it's important that you have the right inertial tensor for those values. So you need to compute these quantities from the impulse with respect to the current configuration of your object. Yeah. Well,
yeah, and the question is, should we use the inertial tensor, this one, the current one, as a rotation matrix, inertial tensor, rotation matrix transport, just rotation matrix, and inertial tensor?
Also, it's both, definitely, right? Because
both,
yeah.
Because we used the rotation matrix transpose on the other side, because after that we multiplied it with angular momentum. So we brought angular momentum to the rest state, multiplied by inertial tensor in the rest state, and after that brought back to the current state.
Exactly. Yeah.
And this is this one.
Right. Yeah. You can think of it as a unit. You always need to transfer into the rest state and back. Because in a way, also this equation you evaluate in your current one, the current state of your object. So right, you can think of this as a unit. You always need both transformations. Yeah. Right.
The last question is about still left-handedness, right-handedness in our exercise. It's written that there is some wrong metric calculation in provided repository, and that we're supposed to replace it by some file from the archive, but there is no archive. Oh,
can you also contact the tutors or our exercise team, Brenner? But I'll double check with them. I have to admit, I was not informed of that. Or have you already contacted them, or did you? Yeah.
It's written that please use the new metrics file in games physics exercise zip file, but there is no archive in Moodle or somewhere else.
Okay. Please directly also send an email to Brenner, and I think you can fix that. Yeah. Okay. But I'll also check with him. Yeah. I hope that this is already fixed, but right, I don't know the latest status of that. Yeah. All right. Thanks for joining.
One last question about forces. Should they be applied like all the time to the body?